The data set that I'm using comes from the University of California at Irvine Machine Learning Repository. And that's the UCI Anteater right there. And this one is called Default of Credit Card Clients Dataset. And it has 30,000 cases. That's the number of instances. And it has 24 different attributes. And this tells us who donated it, the original purposes, and it describes what the variables are. Now, I've taken most of that information and I've repeated it in a text file that's included with the assets, Default of Credit Card Clients Dataset, where I give the URL that it came from, copy that information. And then at the bottom, I did a few things. First off, when you download the dataset, it comes as an Excel file, and it has two rows of headers, one with sort of cryptic names for the variables x1 to x25, and a second row at the top with more descriptive names. I got rid of the x1 to x25, left the full variable names. I converted the XLS Excel file to a CSV file, and I renamed it CC default for credit card default.csv. So here in RStudio, the first thing I'm going to do is I've decided to use a KNN, which is a K nearest neighbors algorithm for doing my classification in this one. What that does is it looks at all of the cases that are similar to the ones you're trying to decide whether they would, for instance, be defaults or not. It looks at the ones who are similar to them in many other variables, and it really takes a majority vote of whoever's closest. It's a very conceptually simple mechanism, and so it's the first one I want to demonstrate. Now, I'm going to be using the KNN function that's from the package class for classification. And I'll use the pacman command to load that. And so we get that loaded. And then I'm going to read the data set. Now I've copied the CSV to my desktop. So this will read it right off of there. I'm going to feed it into an object called df for data frame. And you see that's now loaded. It's got 30,000 cases in it. Let's get the column names very quickly as a way of assessing that we got the right stuff. I'm going to zoom in on that. And you can see we have 25 different column names from ID, which is the ID cases. Then we have the actual predictor variables. And then the very last one, number 25, is default. That's whether they defaulted on their credit card payment. Let's also take a look at the first 6 cases by just using head. And I'll zoom in on that again. And then you can see what kind of numbers we have on each of these. I'm not going to do anything special with that right now. Now, normalizing the data is an important step in a lot of multivariate analyses, including classification. If the ranges for your variables are very different from each other, so one's a 0 to 1 and others 0 to a million, it's a good idea to normalize the variables. That puts them into similar ranges, and it makes it so the algorithm doesn't give undue emphasis to the variables that have the larger ranges. In fact, let's take a look again at my first few cases. And you can see, for instance, that sex and education and marriage are mostly 1s and 2s, and that age is age. And then you've got a bunch of variables that go from sort of -2 to +2. And then you have financial ones, which get up into really big numbers. And then the default is back to 1s and 0s. So we do have very different scales. And so normalizing would be a good idea in this case. Now, there's a lot of different ways to do this. One is to take the z-scores, or standard scores. I'm going to do a little shortcut that's used more often than that. And that is simply to look at the range of the scores as opposed to the standard deviation. And we can create a function here. So we're actually going to load this function. We write it for normalizing. And all it does is it takes the range of the scores and finds out how far a score is in that range. And so it gets to be a proportion of how far up it is from the bottom. I'm going to run that command. And what that does is it actually just saves it as an object over here in the environment. It says I've now got a function there. Let me zoom in on that just for a moment. I've got normalize. It's a function. There we go. So let's go back to where we were. Now what I'm going to do is I'm going to use that new function we just created, normalize, and I'm going to apply it to the data frame, but I'm going to specifically exclude the first and the last columns because the first column is the ID numbers. I don't need to standardize that. And then outcome, I want to leave that alone. I want it to be 0s and 1s. So I'm going to do that and save it into a new object called DFN for data frame normalized. And then we can take a look at the first few cases of that. And, now that we've done that, we've got lots of decimal places, but now you see that things all are in the 0 to 1 range. So that's consistent and that's nice. On the other hand, we lost the outcome variable, whether a person defaulted or not. So I'm going to put that back on using the cbind or column bind function. And then because it sticks it on with the df command for its name, I need to change that name back to default. We can look at the column names to make sure I did it all right. And that looks correct. And then we can take a look at the first few cases. The important one being this last column here, default, ones and zeros. That looks good. Okay, what we need to do now is a way of testing how well our classification works. We're going to split the data. We're going to create what's called a training set. I have 30,000 cases. I take 2/3 of that, so 20,000 cases, and I put them in one group, and I take the remaining 10,000, I set them off to the side, and I do my statistical modeling on the training set. And then I take the model that I create from that and I test it on the testing data to see how accurately it can categorize those cases that weren't included in the original model development. This is a cross-validation, and it's a really good way of making sure that you don't fall into overfitting or making a model that's too specific to the data you're developing it on. I'm going to set a random seed here so it's repeatable, and I just picked a number 2786. And then I'm going to split it. I'm going to take the entire data set. I'm going to split it into 1/3 and 2/3. Or really what that does is it creates a new sample column that indicates that. And now I split it, but I exclude the outcome variable. So this is the data without the outcome. I create DFN, or data frame normalized training data, and then the test data. And if I look over here in the environment, now you see I've got this one. It's a random process, so it's close to 10,000 and 20,000, but there you have that. I also need to create variables that have the outcome labels, but keep them separate. So I do that for the training cases and for the testing cases. Now what I'm going to do is I'm actually going to build the k nearest neighbors classifier, and then I'm going to test it with my cross-validation holdout sample. So here's what we're going to do. We need to build a classifier for the test data. You get to choose a value for k. How many neighbors do you actually want to compare? You generally want to use an odd number because it avoids ties. And truthfully, you can try a lot of different values, just kind of bounce around and see how that affects accuracy. This is the general command. I'm going to save a predicted model here using the knn command. And I run it down here. I also have to indicate the true class really so it knows exactly what category they're supposed to be in. And right now I'm going to use a value of 9 for k. For each data point, I'm going to compare it to its 9 closest neighbors and sort of vote and see if those are default or non-defaults. So it's done that now. And if we look over here, I've got yet another object over here. And really the critical part here is creating a table that compares my predicted defaults to the actual defaults in my testing data. And do that right here by running this command, and it just prints it right down here. And as you can see, for instance, these are the predicted. 0 is for not a default and 1 is for yes. And these are the actual outcomes, 0 and 1. And so you can see, for instance, that we have 7,249 cases that were accurately predicted as not defaults and 737 that were accurately predicted as actual defaults. These ones that are off the diagonal are errors. We have false positives and false negatives. Now I'm going to do this just for a second and change the value of k. Let's pick a bigger one. So I'll go to 21 and we'll do this again. I'll just run this command right here. It takes a moment. I'm just waiting for it to catch up. It's a lot of calculating when you have a big data set and you're doing a lot of neighbors. There's a lot of distance calculations. But let's run the table here. And I'm going to zoom in on the output. And what you can see is interesting is we now have more accurately classified negative cases. We've gone from 7249 to 7360. So that's an improvement, but we've reduced the number of true positives. We went from 737 accurately classified defaults down to 707. So what's funny about this is even though we may have an overall better fit, it does it at the cost of losing the true positives. We have more true negatives, but this is probably a trade-off we don't want. And so this is a curious situation where choosing a lot of neighbors is probably not the best idea. We're probably better off staying with 9, what we had before. Anyhow, that's a very simple run through of how k-nearest neighbors can be used as a way of testing a model on a data set and then comparing it and validating it with a holdout group. It's a neat way of seeing how you can classify new cases and give you some indication of the validity of the classification system that you're building.